Part 25M, Color on the Flat Earth. Why is color so important? Because color tells you the temperature of light or a flame. Harken back to middle school, general science, and the Bunsen burner. The color of the flame tells you the intensity and temperature of said flame, yellow being the coolest and blue being the hottest. The plasma tube of light is tightening due to angular momentum and the increasing electromagnetism and magnetic fields. As the energy to our cell increases for the EMPCOE, the fields increase and the plasma tube of light is forced to travel in a tighter spiral. The plasma tube of light was wide and has got more narrow. And will continue to get more narrow until it becomes a single highly focused ray of light, or laser-like. As it tightens, it increases in temperature and intensity. 1000 degrees Kelvin equals 727 degrees Celsius. 1000 degrees Kelvin equals 1340 degrees Fahrenheit. The orangish yellow at the left is 1000 degrees Kelvin. The color changes from left to right, from dark yellow, orangish yellow, to lighter yellow, and then white, then bright white, and then blue tints coming in, and then all the way to the right-hand side of the blue light is a temperature difference between 1000 and 10,000 degrees Kelvin, from yellow light to blue light. Tangent. That is why they have been very subtly changing the light bulbs you buy. Light bulbs of old were yellow light. Then they switched them to white light. And now they're moving to bluish tinted light. So the brain dead zombie masses get used to white light and then blue light, also known as conditioning.
Some so subtle you might not have even noticed, but your brain did.
The yellow sun. Diffuse, cooler. The color of the sun until the early 2000s. The white sun. Less diffuse and hotter. The sun of today. The blue sun. Extremely narrow and mega hot. The most important sign of the EMPCOE. Here, let me show you what an extremely narrow beam of blue light, or laser, can do. if 10,000 degrees Kelvin has you worried. From just an extremely narrow ray of blue light. See what happens when you add a lens.
Okay, so you can see it's kind of a line of light now. And it's kind of burning the background here. Now let's see what happens if I stick my lens in front of it. Whoa, I can make it a tiny point, and it easily burns the background now. So you can see the smoke coming off of it. It's slightly burning the background here, but then as soon as I put my lens in there, I can focus it down to a tiny little point. And it immediately burns whatever's around it. So you can see that it kind of starts to burn the wood here. It takes a while for it to burn. Have to leave it there for a bit because it's far away across the room. But now watch what happens when I focus it down. It pretty much immediately burns and starts on fire. It's awesome. It essentially just etches into the wood immediately. And you can see that this happens even more powerful than if I had the laser just right up next to it. You can see that I still have to leave it there for a bit to even start burning. So it seems as though I get my highest temperature when I put my laser really far away, essentially so that I get that little tiny laser slit to a single point because I place it far away. And so that all of the light coming from the laser is now focused into a very, very tiny point. And so all of the energy from the laser can be focused to a small point due to the magnifying glass. And so you can even get a higher temperature than if you just placed your laser directly on the thing you were trying to burn.
Do you see the focal point converging from a lens in the Death Star now? Or conditioning?
Some so subtle you might not have even noticed, but your brain did.
Don't forget, we have two lenses above us, the ice dome and the waters above. The magnification of light and heat through optics. And now you know why I said the plasma and the sun to ignite in part 25J. Next video, part 25N, plasma tube of light on the flat Earth.